So if we take a look, gas particles are far from each other, and as a result, gases can be compressed. They're one of the only ones that can be compressed. If volume goes up, pressure goes down. We are saying that these are what we call inversely related. If volume goes down, pressure goes up. Now, temperature and pressure are directly related. If temperature goes up, pressure goes up. If temperature goes down, pressure goes down. Why? Well, volume, when you put the squeeze on it, the particles can hit the walls faster. So they bounce into the walls faster. With temperature, if we increase temperature, those particles are going to be moving faster and colliding more often. So that's why the pressure goes up. Combined gas law puts all of these things together. P1 V1 over T1 equals P2 V2 over T2. The ideal gas law relates number of moles or number of particles to the pressure, volume, and temperature. The label for pressure, if you're going to use 0.0821, pressure needs to be in atmospheres. Volume must be in liters. That's the moles of the gas. So if they give you grams, you got to change it to moles using the periodic table. And temperature must be in Kelvin for all these. All these gas laws require kelvins. That's the quickest way to mess up every problem, is not bother changing from Celsius to Kelvin. STP stands for standard temperature pressure. The conditions for that are 0 degrees Celsius or 273 Kelvin, and 1 atmosphere or 760 millimeters of mercury. 1 atmosphere equals 760 millimeters of mercury equals 101.3 kilopascals, 760 torr or 14.7 psi. The main ones you need to know here are 700 millimeters of mercury and 1 atmosphere. Pressure is caused by the gas particles colliding with the walls. Absolute zero is 0 Kelvin or 273 degrees Celsius. Kelvin plus 2, Kelvin minus 273 is Celsius. This would be negative 273 degrees Celsius equals degrees Celsius. Degrees Celsius plus 273 equals Kelvin. Blank is the result of all the air being pulled in by the Earth's gravity. Atmospheric pressure. That is atmospheric pressure. All right. We answered these problems on the other video. So if you want to get these down, you can watch that. The bigger ones are like effusion and diffusion. Yesterday we talked about the LA, the cranks spray, the particle being big. So it takes a long time for it to move versus a smaller particle moves quite quickly. The reason for that being is that kinetic energy is related to mass and velocity. The smaller the mass, the faster the velocity has to be. The bigger the mass, the less the velocity has to be in order to have the same kinetic energy. Remember, kinetic energy is like a measurement of temperature. So temperature is a measure of the average kinetic energy. So they're directly related there. Let's take a look at these guys right here. A specific quantity of an unknown gas. See if I can zoom into that a little bit. Specific quantity of an unknown gas. Let's put that picture down. Has a volume of 14.3 liters. 22 plus 273.
The answer is 295.
659 divided by 760.
The answer is about 0.8671.
So I want to make sure that these are in Kelvin and these are in atmospheres. And I want to calculate that volume at STP. So that means I need P1 V1 over T1 equals P2 V2 over T2. We're calculating the volume. So I need to multiply both sides by T2 and divide both sides by P2. T2 goes up, P2 goes down. And now it's just a insert and calculate. So T2 is 273 Kelvin. P1 is 0.867 atmospheres. V1 is 14.3 liters. 14.3 liters. So then we're going to divide all of that by P2, which is 1 atmosphere, and T1, which is 295 Kelvin. Whew. Atmosphere cancel out, Kelvin cancel out. And we just plug it in. 273 times 0.867 times 14.3 divided by 295.
It's about 11.4734.
11.5 liters. If we take a look, the temperature went down, so the volume should go down. The pressure went up, so the volume should go down. So that makes sense. It goes from 14.3 to 11.5 liters. 6. At what temperature in degrees Celsius will a 2.5 mole sample of CO2 gas exert a pressure of 1140 torr in a 20-liter container? 1140 divided by 760.
It's 1.5.
So that's 1.5 atmosphere. So we have PV equals nRT. Now, if you're questioning how I know it's that formula and not the P1 V1, it's because we have the number of moles here. If we're given moles or grams, we have to use this equation. We want to find the temperature, so we need to divide both sides by N and R. The pressure I just calculated in atmospheres as 1.50 atmospheres. The volume is 20 liters. The number of moles is 2.5 moles. The R constant, that's why I converted that to atmosphere. So I can use my R constant of 0.0821 atmosphere liters per mole Kelvin. Atmosphere liters will cancel, moles will cancel. 1.5 times 20 divided by 2.5 divided by 0.0821.
That would be about 146.1632.
Now that is in Kelvin because the unit Kelvin in the constant. 146 minus 273.
The answer is negative 127.
They want in degrees Celsius, so I have to subtract the 273 to get negative 127. A 251 liter sample of a gas at STP is heated to 45 degrees Celsius. The final pressure is 1.10 atmospheres. Calculate the volume of this under the new conditions. So all of this is our ones, our initials. That's our V1, there's our T1 and our P1. Here's our T2, 45 plus 273.
The answer is 318.
So there's our T2 and our P2. We are looking for V2. Again, since they say new conditions or the final pressure, that gives us a hint that we're using the combined gas law instead of the ideal gas law. We're trying to solve for V2. So we need to multiply by T2 and divide by P2, causing them to cancel out. T2, well, is 318 Kelvin. P1 is standard pressure of 1 atmosphere. V1 is 251 liters. P2 is 1.10 atmosphere. T1 is standard temperature, so that's 273 Kelvin. 318 times 1 times 251 divided by 273 divided by 1.10.
The answer is about 265.7942.
265 liters. What is the pressure of a 10-liter flask containing 0.75 moles? So keep in mind, if they would have given us grams, we would have had to go from grams to moles before doing this. They were nice. They gave us moles. That is in 26 plus 273.
It's 299.
Here's our volume. PV equals nRT. What is the pressure? So we're looking for P. We need to divide both sides by V. Moles, 0.75 moles. R, I'm going to do R in 0.0821 liter atmosphere per Kelvin mole. That'll give me my pressure in atmospheres. T, 299 Kelvin. Kelvin and mole will cancel out. Down here, we're going to have liters to cancel out because it is a 10-liter flask. 0.75 times 0.0821 times 299 divided by 10.
It's about 1.841.
Two significant digits. 1.8 atmospheres. Cool. Let's take a look at one other type of problem, and then I'll let you work on these alone, and then you can always check the answers and stuff like that. But let's imagine we have methane gas, CH4. We're going to react that with oxygen. That's going to yield, like any other combustion reaction, carbon dioxide and water. We need to make sure that it is balanced. We have 4 hydrogens here, so we need a 2 there. 1 carbon, 2 oxygens. We have 4 oxygens over here, so we need a 2 there. Let's say we have 30.5 grams of CH4, methane. I want to figure out how many liters of oxygen I can get. And all of this is going to occur at STP. So by using this balanced equation, we know for every 1 mole of CH4, let's do this. Let's find out how much CO2. No, let's do oxygen. How many liters of oxygen needed to react? We have 30.5 grams of CH4. 12.01 plus 4.04 is 16.05 grams for every 1 mole. That's from the periodic table. If you don't know where that came, 1.01 times 4 plus 12.01. Every 1 mole of CH4 requires 2 moles of oxygen. Remember, that's O2. Since this is an STP, every 1 mole of any gas at STP equals 22.4 liters. So every 1 mole is 22.4 liters. That's what we want. 30.5 divided by 16.05 times 2 times 22.4.
It's about 85.1339.
we would need 85 liters of oxygen to react with 30.5 grams of CH4. Do you have any questions about the review that you need me to cover?
The last question you just did, is it all the moles, 22.4 liters?
Add
I think
STP, yes.
okay.
1 mole of any gas, add STP, takes up 22.4 liters of space. Yep. Doesn't matter if it's CH4 or O2, as long as you're talking about a gas. So if you had, let's say you had 1 liter of 5 different gases at the same temperature and same pressure, the one thing you can tell us about that is we'd have the same number of particles in all of those. If the pressure and temperature are constant for these gases, if they're all the same volume, they have the same number of particles. If they all have the same number of particles, they have the same volume. It's universal. If temperature and pressure are equal. Others? All right, then I'm going to put this video up there, and I'm going to put any other answers that aren't on there for you guys. If you do have questions, I will keep this Zoom open. I think one of you is staying after so we can talk about the laboratory. So that's definitely fine.